Good morning, everyone, and thank you for taking the time out to join us for this series of Koita Center for Digital Oncology series of webinars. So what we hope to do through these webinars is to explore certain aspects of digital health and try and familiarize us with what the landscape is and to share those details with you. And today we really are fortunate to have two pioneers in their respective fields in digital pathology, which is such an integral part of not just cancer care, but overall healthcare in itself. So pleasure to welcome Dr. Joy Mammon from the Christian Medical College, Vellore, and Dr. Swapnil Rane from the Tata Memorial Hospital. And I look forward to hearing from them about their experiences and especially some of the areas in digital pathology that they have worked on. Before we start with that, I'll just request Nikesh to update all of us on some of the other initiatives that the Koita Center for Digital Oncology has been focusing on over the past few months and update us on that. Over to you, Nikesh.
Okay. Thank you, Dr. Pramesh. And again, welcome everybody. Just a very quick update. I think when we met last time, we had spoken about, or we have been speaking about the oncology specific EMR. And we had 4 hospitals at the time that had already become part of the what we call as the LEAP program, or the Leading EMR Adopter program. I'm just happy to report that we have 10 additional hospitals that got funded through the program. So our count has gone up to 14, and we have 6 other hospitals that are also close to confirmation. So I think by the time we meet next, we would have had 20 hospitals that would have gotten funded through this initiative to implement one of the 6 NCG empaneled EMRs. And then we've got another pipeline of about 10 hospitals. But I just wanted to request all of you guys that if you haven't or your organization hasn't yet applied, please go ahead and apply. And if you know of anyone that you think would benefit from having a oncology specific EMR, please refer them to us. We are continuing to fund the initiative. We've secured some additional funding as well. So that was my second update, that we've got a good CSR grant from Axis Bank to fund many of our NCG initiatives, including a lot of the digital work that we do. So it's great to have a reputed bank trust or put their trust in the work that we are doing. Very important work and will take time to deliver value, but that just allows us to plan a little bit from a longer term perspective. So that's another good news that I wanted to share with all of you. And then finally, a couple of other things that we are now working on. We are just experimenting with revised operating model for telemedicine to see if we can industrialize that. And then if it's successful, we will bring that to this group in terms of how do we roll that out across our network. And then there are a couple of other initiatives like synoptic reporting that we are looking into as well. So lots of things in the hopper. I think as some of those things mature, we will reach out to you and engage with you both in terms of getting your feedback, but more importantly, also share the benefits with you and find a way to scale those initiatives across our network. So with that, let me turn it over to Dr. Joy Mammon, who's going to talk about the interesting work that he's done on the digital pathology side. So Dr. Joy, over to you. And you can all ask questions in the chat if you'd like, or we will have some time after both Dr. Joy's presentation and Dr. Swapnil's presentation to take questions.
Thank you. Thank you, Dr. Shah, and to Dr. Pramesh for the kind introduction. I will share my screen. So today's presentation and discussion is part of an earlier conversation I had with Dr. Shah and with Swarlaka. And I'm really happy and privileged to be presenting this to this group today. This is not a finished task. As I mentioned over there, it's a view from the trenches. We've gone through some challenges while we were implementing the solution. And so today is a discussion of what the issues were and what people should be aware of when we go into digital pathology. I work as a pathologist in the Department of Translation Medicine, which involves blood transfusion services, as well as clinical pathology, lab hematology, hemostasis, and immunogenetics as well. I'm indebted to the general pathology department. We are separate departments here, but they have included me in their project, and I've been working with them to implement the digital pathology solution over here. I work at CMC for the last 23, 24 years, also had some training in pathology informatics from the US somewhere early in my career. So to go on to our discussion today, CMC Vellore, 123 years old. We are located in the south of India. On the top left is our main campus, and this is the old campus. Some of you have visited here. This is the new campus about 10 kilometers away, which is the main reason why we have been able to leverage the digital pathology solution with our administration. Our campus here, this campus where I'm sitting right now, is the main campus, and it's 100 years old, about a month ago. Just a snapshot, we have more than 3 million outpatients and about 140,000 inpatients over the last year. And the total number of beds are just over 3,500, and they keep fluctuating every now and then. We have multiple campuses, but the main campuses where we are functioning is the town campus, Ranipet campus, and Chittoor campus. So today we are going to talk for the next almost just over 10 minutes. We're going to talk about why pathology imaging is different from other imaging specialties. Then what went into making our choices, what are the building blocks that are important, what are the challenges that we face, and what the future prospects are. And I do not have any conflicts of interest today. So usually we are compared with the radiology department. So I'll just take you through the radiology workflow. We're all familiar with this by and large, just to keep us focused. Traditional radiology workflow, where the patient visits the doctor orders the X-ray, it's done. It used to be on film, so the was developed, filed or handed over to the patient. The patient sees the doctor with it. And then at the end of it, either the X-ray film is filed or it's handed over to the patient. So just the basic workflow that we take. What happened after digitization? Once the doctor has ordered the X-ray, the film, the image is done. Films are usually only on demand. The images are kept on a server. Long-term storage is managed. Patient sees the doctor with the digital image, and then sometimes they can ask for a print and they get it on. How is pathology functioning? This first column is our traditional workflow. Patient visits the doctor, the biopsy is done. There is a whole huge workflow inside this one box over there, where the tissue is selected, appropriately sampled, processed, paraffin blocks are created, thin sections are made at micron thickness, and then they are impregnated with various different types of stain for contrast, different types of processes like fluorescence can be used. And then finally, the sent to the pathologist for examination and reporting. The blocks and slides are filed, and reports are sent to the doctor with the patient. Now, in the digital world, what has changed? All the earlier touch points still continue. In addition, we have this option of scanning and storing. So it's only after everything is done, after the slide preparation, work is happening. Then after the slide preparation, we are scanning. So there is an important difference between what radiology does and we do. And that is important to appreciate. And the advantage for digitizing radiology is no more wet films, no consumables, no physical storage, no transport, no loss, no hidden costs, and teleradiology is possible, consultation is easy. And disadvantage, of course, depending upon your scale of operations, you'll have to spend for server storage, peripheral hardware also. For us, this was an important watershed moment in our institutional history. We implemented a GE centricity solution in 1998, 99. It was funded partly through a USA grant. It cost almost $1 million at that time. But what happened was that desktop computers appeared across the outpatients and inpatient areas, which drove other changes subsequently. In terms of pathology imaging, what are the digitizing? What are the greatest advantages? Slides are easily retrievable, and quality of slides in terms of stain contrast remain because we have digitized it, and there is no loss or misfiling. However, future developments are also promised, but there are significant disadvantages in terms, especially of the whole process still remaining. Remember, all this can happen only after you prepare the slide. And so all manual processes remain, and this is an added cost on top of it. The patients really are not interested whether we have diagnosed their conditions or reported their disease on a digitized slide or whether we did it on the original traditional microscope. And then all the other added costs beyond this. So it took several years for us to make these decisions. And the key driver was the multi-campus mode. We had to choose which scanner. We had to make sure that we had the right resources for it, whether it would be housed centrally, whether how the interfacing would happen, where would the data storage happen, what would be the volume that we could accommodate, what would be the image format. Earlier applications had proprietary formats which could not be opened with any other generic program, and then we had to make sure that we did not lock ourselves into a particular application. Many of these programs came with their own workflow. There was an important question whether the company would be able to change it based on our own requirements. Of course, histology quality remained at the heart of all this, and I mentioned that later. And we also needed to have a change in practice of work by the pathologists. And of course, at this point, there is really no ROI yet on what we have implemented. Before we go digital, there are important foundations that we must have, and it is preferable that we have a HIS so that and an LIS so that all these steps can be automated and you are already realize the benefit of an automated workflow before you go on to implementing a digital workflow, especially as far as imaging is concerned. So for us, a lot of this has happened inside our own LIS. And we were at the stage where we were reporting through the LIS. We've used Dragon for many years now for transcription by the pathologist. And reports are signed out into the hospital information system from where the doctor discusses the results with the patient and a report is given. This 2D barcode on a slide was a new addition which we had done this time. And I will show you what the results are there. So one of the things at the heart of all this is that our histotechnology should be sound. Earlier, it was good enough to have good quality of slides, but now I think we have raised the bar. We should have excellent quality of slides because thereby every preceding step from the time that you choose the tissue section to be sampled and all the processing steps, embedding, cutting sections, everything becomes important because otherwise the old principle of garbage in and garbage out applies. If you don't have good sections, then you get to see highly magnified in great detailed junk sections with folded tissues or air bubbles and all those things magnified in great detail and stored at great cost. So we should be careful about that. Even white space between the tissues will get accounted for in your scanning. So when we talk about scan times and scan speeds, remember the adage, the standardized term is 1.5 into 1.5 centimeter sections scanned at 20 or 40x will produce an image of 1.5 to 2 GB. However, if you have larger sections like this, and with larger spaces in between, all of this becomes one image, and therefore your image size increases. It is challenging to put a one-dimensional barcode on this, so we decided from the beginning we'll have 2D barcodes, positioning it appropriately, replicably, reproducibly, and also making sure that the skew of the barcode is not too much that the machine can't read it. With this, the machine can read the barcode during the scanning operation, create metadata around it, and create a folder for storage of the images. So our current platform is from an Indian company called OptraScan. They're based out of Pune. And we have a multi-campus mode on 2 campuses with one single central server located on one of the campuses. Our campuses are connected by high-speed network that we have implemented. Image path from OptraScan is their application. There's 2 parts. One is the image acquisition mode, then the image viewer and management modules. They also have a workflow management system, which we do not use. We report and we manage our workflow from the LIS. So we use the Optra systems for image acquisition, storage, image lifecycle management, and also for viewing. We have gone with an on-premise mode for image storage. OptraScan offers a cloud-based solution with their preferred vendor. We use a hyperconverged infrastructure from Nutanix, storage from Cohesity, and offline storage with IBM Taper. Some of these, the last part has not been implemented yet. We are still using Nutanix and Cohesity right now. Our interface was developed by CMC IT team. We decided that it will be highly, the workflow will be tight and will remain within our control. These are the devices that we have. This is in our main campus, the Asha building, the 4th floor. And these are in the new campuses in Ranipet. This is the OS 160. and this is the OS15. This smaller one was designed specifically for using it on frozen sections as well. So the workflow, accessioning, all this is traditional workflow. And after we finish getting the slides, currently we're doing an archival workflow while we're waiting for pathologists to get familiar with it. So after the pathologist reports, there is a request for scanning by the pathologist. The scan work list is created, the slides are moved to the technician, the work list is sent to the image path server, after which the scanning is done on the scanning workstation, images are uploaded to the server. Then there is a QC check by the technician, and the pathologist can view the images through a URL, which is embedded inside the pathology workstation. So I'm just showing you only one screenshot. I'm not going to show you details of it, but all of this happens from within our own pathology workstation, which is our LIS for our pathology work. So there are bidirectional interfaces through APIs. The scan is ordered by the pathologist, work list is created, images are uploaded to the server, and we have an opportunity to rescan if the quality is poor, as decided by either the technician or by the pathologist. There is a licensing for the viewers, and all the authentication happens over the APIs within the interface. We don't have to log in separately to each time that we want to view the image. So some of the challenges that we had is to decide whether we wanted to do on-premise versus cloud. We decided on-premise because traditionally we don't have a policy for storing patient images on the cloud. We're working towards that. Image format was JPEG 2000, which has a somewhat lossy compression, but it was enough for reporting. The slide volumes, the image volumes are very high, as you all know in pathology, ranges from 1.5 to 2 or more gigs, depending upon whether you're doing at 40x scanning or 20x scanning, also the size of the tissue and the white space on the image. So those are all challenges that we need to face. We produce more than 1,400 slides a day across both the campuses. So we are not ready for forward digital workflow. We'll do that gradually, and I'll show you what our plans are. We are able to collect the metadata and annotation data from the system. We are working on getting the annotation data. Metadata is already being transferred. We want a vendor-neutral archive. The image formats are standard, and the database is MS Microsoft is what is used for the database management system. So we think that we will be able to manage that. We need to work on the image lifecycle management policies. In our Nutanix server, we use the S3 buckets like Amazon does. So we are kind of ready to move to cloud whenever we have to. So now we have to work on the validation for clinical use. There are no current regulations, and I know that the new 15189 from NABL will, the 112 document from NABL will also include digital pathology in its future avatar. There are some publications I've listed here. There are already guidances earlier from Pathology group in archives talking about how to validate a digital workflow. And more recently, a concept paper has come out from CAP for use of images. We have had various challenges, and just summarize them on this slide. It has been challenging because, for one, we are not used to remote support and remote workflows. So that is something that takes getting used to when maintaining secure VPN-based connectivity and people over here to make the necessary physical changes while the IT changes are happening. Interface development took some time because this was a new product, and developing the interface manual and getting used to that also took time. Also, getting used to this new paradigm, digital over analog, is challenging. People have to get used to it. Now, more and more platforms are available. People are using it for equals and quality control and for certain examinations. However, we also need to rethink this pathologist workstation based on the new workflow, and those are upcoming challenges for us. We do currently archival scanning just to get people familiar with it. So pathologists can choose which slides they want to scan to archive. And this also gives some time for pathologists to get used to this idea. And sorry, that's a wrong. There's a typo there. We want to work with some champions to start off with operational digital workflow. We also do education and postgraduate training on this. We also do project scanning based on demand. We are hoping that we'll be able to integrate it. We have our own Moodle Plus task-based CMC learning platform. we're hoping to implement that for a solution here. The system allows for consults and telepathology. We have to work with our IT system to allow access into our server so that we can enable that. And multi-department meetings. The future is evaluation of inbuilt tools with objective IHC evaluation. There are already applications of algorithms available for these, and then research and development. We'd like to see ourselves not only as image providers or data providers, we'd like to have local capacity developed. And I will close with that. I'd like to thank the team at CMC, especially in pathology department and IT team, OptraScan and Koita and CG for this opportunity. Thank you.
Any questions for Dr. Joy? I had a couple of questions, but I'll let the audience go first. But thank you, Dr. Joy. That was very insightful. I know we had little time. You packed in a lot of information in that time frame.
Can I ask a question?
Yes, Dr. Swapnil, of course.
Hello, Dr. Maiman. So have you visualized what happens tomorrow when you want to buy another scanner from a different company?
Yeah. So I mentioned vendor neutral archive in this. We have not worked out the details of this, but like I mentioned, the application supports JPEG 2000 as the base of imaging. The server is ours, the storage is ours, the database is accessible to us. So in principle, I do not think that there will be issues as far as integrating another archive is concerned. Of course, we've not talked to the company before, but that is our dream going forward, that we should have a vendor neutral archive so that we can implement as many solutions.
So vendor neutral image management systems like the PACS is also what possibly will help in that direction.
Correct. And I think currently DICOM has a working group for pathology, but I don't think the specs have been put up yet for slide images. There's some draft.
DICOM is still a bit far away.
Yeah.
So at least in the short term, viewing solutions which can see multiple image types.
Dr. Swapnil, if you have any thoughts on the prior conversation on how to connect all of this, you can respond to that and then jump into your presentation. I think that'll be a good segue.
Sure, thank you. Yeah, I mean, digital pathology is the base of what is going to happen in the future. Digital pathology itself is going to evolve gradually as things change, as the DICOM standards come in. And to be frank, the way we digitized slides at this point of time is going to remain for the near future. But there are a lot of new technologies being developed which potentially challenge how slides will disappear. So just like the radiology film disappeared largely from practice and everything went digital in a paperless mode, the glass slide today is irreplaceable. We still need it for digitizing, and that will be there for the next probably a decade or two. But perhaps there are some technologies that are still in the early phases where whole block imaging and whole block almost micro CT scan like and virtual staining of those imaging with 3D reconstruction are in the early stages, and hopefully if they are taken ahead, they might replace the glass slide in the future. So it's a continuously evolving domain. In the current scenario, vendor neutral image management systems is obviously going to be the way to go. It's like we don't really talk about which company we are buying the microtome from or for the staining machine from. Similarly, to maybe in the next few years, if people adopt vendor neutral image management systems, then we won't have to really talk which scanner to buy or which company I should take the scanner from. It wouldn't matter at all. In my mind, the digitization, the scanner is essentially the microtome of the digital world. It is just that, and that is how it should become. Regarding the online and offline or the cloud storage versus on-prem, there is practically no difference apart from the assumption that this is not on the cloud that we typically talk of, AWS the IBM and other things, then is essentially that we don't have it on our premises. That is the only difference. Essentially, it's some computer sitting somewhere on which you are storing that data. To many of the current online of on-prem storages also offer most of the benefits that cloud storage offers. And if you're a small operation, cloud storage makes a lot of economic sense. But if you're a large operation with multi-centric kind of operating system, then perhaps a centralized storage on-prem makes more sense. And just like you said, the hub and spoke model, where a number of related hospitals or related centers can come together and set up a centralized storage on-premise somewhere and then go ahead. But for small operations, cloud storage makes perfect economic sense as far as diagnostic digital pathology is concerned. So that is what my thoughts are on digital pathology. As the diagnostic, simply replacing the microscope with the computer screen. Yes, Dr. Mem.
Can I just add a comment to that? I completely agree with the statements that you have made today. And I think we should work towards that. Two things. One is that we have to recognize that every step that I said is a challenge, is an opportunity for partnering with research organizations, with vendors. So I think having groups that have these cross reactions are very important. Otherwise, we'll be sitting forever moaning about what our problems are, compressing images, storing images, moving all these things back and forth, creating vendor neutral archives. All those things are important. We should start having these conversations. We should not be making the mistake of siloing ourselves and then not reaching out to technology people who have solutions and are unable to reach to us because they have. So thank you very much. Once again, thank you to the organizers for this opportunity.
Right. Thank you. So I'll just jump to the next part of it. Dr. Mammon has set the stage for me to talk more about the uses of digital pathology beyond diagnosis. And I'm going to largely skip a lot of the digital pathology things that I was going to talk about. Okay. So we are going to largely talk about AI. A lot of the work that we are doing at TMC, along with our collaborators in multiple centers in the country as well as outside the country, I'm going to try and present a few of them. And obviously, there are certain things that we have not done. I'm going to talk about it, but largely to give a sense of the direction in which the world is moving in this digital pathology and AI space. So all of this we know, and I'm going to kind of skip a lot of this digitization part of it. And we know obviously that we have to validate the diagnostic process on the digital platform before we adopt it. One thing that I would like to highlight to the audience is that the complexity of the pathology file format that is generated. So it is essentially not a single image. It is actually a package of thousands or perhaps lakhs of smaller images put together in a pyramidal fashion, pretty much like a Google map, wherein the level of detail depends upon how deep you have zoomed into the image. So if you're looking at an image at low magnification, you get different kind of details. You zoom in, you get more details. If you want to look at nuclear details, you go deeper into the slide, into the image, pretty much like how we do for the microscope. At low magnifications, we look at primarily at the architecture and not at cellular details. So that is why this is quite very similar to how a pathologist looks at slide, and therefore it fits very well into the pathologist workflow, and the adapting process is much simpler. The problem obviously is about the storages, the size of the files. If you digitize an image at 40x optical resolution, you would generate, depending on the tissue size on the slide, 2 GB per image, the compressed image. And if you're a large volume center like TMC, we would generate about 1 petabyte of storage annually if we had to digitize everything. This obviously creates a lot of these challenges, which can be overcome over time. It also presents a lot of opportunities. This is just a slide about the vendor neutral image management system that we have implemented at our center. So each of our scanner has its own storage and servers and its own viewer. But at the same time, we also access the individual servers across two of our centers in Mumbai and Navi Mumbai through a vendor neutral image management system, which then presents us to our integrated reporting platform. So this is how we have integrated it at our level in our two centers in Mumbai. Let me jump quickly to what I am going to focus on. As pathologists, we look at tissues, we look at and at different levels. We look at it through our naked eyes. We note down a few things, the tumor size and things like that. The distance from the margins and other things. Go on to the microscope, look at it in more detail, find out a lot of detail, put in a lot of details about the tumor into the report. Look at IHC, look at genomics, omics, and then merge all of this with clinical information. And to do all of that, essentially, we are trying to have provide a lot of information in various areas, the diagnostics, predictive, prognostic probabilities, and also possibly tell what treatment is going to work on what tumors. As we do more and more of these things, we delve in deeper into tissue. The time and the effort and the money that is required, the resources that go into doing all of this is increasing manyfold. Today, if you have to do a genomic test, it takes about at least minimum of 2 weeks or 3 weeks to get your results. So the time to treatment initiation, if especially the genomic test is going to decide the treatment, is significantly increased in many such tumors. And that obviously has an important role to play in outcomes. And this is a well-known fact that time to treatment initiation affects patient outcomes. A word about the two different types of broad AIs that we are currently dealing with in today's world. All the rage is about the generative AI. It's older and more well-known type of AI, or the discriminative AI, is currently what is being used in most medical setups. So we are still using a lot of discriminative AI. Generative AI is still in its early stages in pathology. There are a few tools that have been developed, but most of the work that is currently happening, most of the areas that are currently being explored, is essentially using discriminative AI. Discriminative means trying to find out the difference, directly differentiate between two or more classes of a particular tumor or a particular protein expression, positive, negative, and things like that. We are not trying to predict the actual protein expression. So broadly, these are the different areas where deep learning or AI ML applications in pathology are currently focusing on. We have simple things that we can do. We can quantitate IHC, we can quantitate tumor immune cells, tumor infiltrating lymphocytes and things like that. There are some automated models that can do diagnosis and classification of tumors. We can actually predict protein expression and genomic mutations using morphology. And also, there are some tools being developed towards guiding therapy and predicting outcomes. So I'm going to talk about a few of these. So quantifying immunohistochemical expression of proteins, like in this case, the MIB1 has largely been a manual task till date. There are now tools that are available, automated as well as semi-automated. And then there are some free tools also available. Like, for example, in this particular case, this is a snapshot from an application called QPath. It's a free software. You can actually use it to do some quantification on your own. And it works on whole slide images. But there are obviously more complex tools that are available that work with, that can allow you to do all of this. So at the bare minimum, you can even start by simply marking out the positive and negative cells, and it gives you counts. But there are more automated ways by which you can do these quantifications. Overall, it has been well established that using computational tools, the accuracy of the pathologist increases significantly. Especially if you have pathologists who have a lower level of experience, who have your early stage pathologists, their accuracy increases much more dramatically as compared to the senior pathologist. Similar to MEB1, you can obviously do a lot of quantification of HER2. This is a known application, and you can now there are tools that can classify tumor versus benign and actually do accurate histological typing. There are some of the tools that we have also built ourselves. Going further, they can even do accurate grading. So now there are tools available for prostate cancer grading, which can accurately quantify the prostate Gleason score. And not just that, but this is not just in a few cancers. There are multiple cancers that this work has been tried out by different people. People have done initially, most of the work has always happened in breast and prostate, but now there are a lot of tools being developed for oral cancer. For this is an example from gastric and colonic epithelial tumors, and in which they have actually shown that the model performs much better than the pathologist as such. And given these are the red dots are the pathologists in this particular chart, you can see that the accuracy of the model actually surpasses the expert pathologists. And another thing that I would like to highlight is the inter-observer variation and the impact of the experience of the pathologist on the level of accuracy. So all of these factors affect the accuracy of the results, and AI models help us to overcome many of these problems, where you can have expert level diagnosis even at centers where you may not have expert pathologists available. All right. Another thing that is very widely worked on is lymph node metastasis detection. There are multiple challenges that were there in the last decade, which accurately detected lymph node metastasis from as small as 0.2 micrometers or 0.2 millimeter dimensions. There are multiple models available on this particular domain. What matters is that what works on your slide. So what we have done is we have actually built our own model, and we have tested it not just on the Camillon data sets, but also on two of our different cancer types. And we are getting a positive predictive value of 0.95 and a negative predictive 0.8. We are in the process of improving this further before actually pushing this into prospective testing for helping the pathologist increase their throughputs. As you would know that most of the pathologists who, when you look at a resection case, if in a head neck in our center, often we have 50 or 60 slides generated for head neck cancer, out of which only 10 slides are pertaining to tumor and the margins. The remaining 40 or 50 slides are still simply looking at lymph nodes and trying to detect smaller and smaller metastases. This is another of our work where what we have done is we have gone beyond simply quantifying protein expression, but predicting protein expression. So in this case, the H&E image is used to predict HER2 expression on, in this case, breast cancer images. This was done on publicly available data set, and we are hopeful of actually converting this into a usable test in the near future. We use the model uses nuclear features and cellular features to actually predict whether this particular area and this particular cell has HER2 positivity features or negativity features. The real advantage of this is that not just quantifying, predicting HER2 expression as 3 plus 2 plus 1 plus or 0, but also being able to quantify the heterogeneity of the tumor of the HER2 expression directly on the H&E image. This would reduce the turnaround times dramatically. Today, to do an IC, you need at least 24 hours of additional time. This we can now do directly on the H&E stain. Similarly, BRAF mutation we have done. This particular concept is applicable to many other mutations also. In this, we have used something called semi-supervised or weakly supervised learning, where we have given the model labels on that this particular tumor is BRAF positive or negative. And then the model has not only predicted the accurately which tumor is BRAF positive or negative, but also given us heat maps on the images where we can actually go and do morphological comparisons as to what area in the slide the model thinks that this is what is pointing towards BRAF positivity or negativity. When we analyze these areas, what we realize is that, that the model is actually latching on to morphological features that pathologists, as pathology, know that they are associated with BRAF positivity. For example, tall cell morphology, oncocytic morphology are associated with BRAF positivity. But now the model can actually use this and quantitatively make predictions as to whether this tumor as a whole is BRAF positive or not. Another work that we have done in EGFR mutation prediction in lung cancer, we can obviously predict tumor versus non-tumor and lung adeno versus lung squamous with very high accuracies. But I wanted to point out a few things, a few issues that AI models face often. One of the things as you can see in this middle table, the accuracy of EGFR mutation prediction on TCGA data and TMC data hovered around 76 and 86%. The maximum test accuracy was 95% in the on the TCGA data set on our models. But the problem is not that you want to test it on a data set. You want the model to be working on every data set. You want the model to work on all your patients, not just on few patients. So when you try and test a model that is trained on the TC data set and you test it on TMC, or you reverse the process, the accuracy is very low. This actually points out to a lot of problems that AI models face in how data differences in the data can affect AI model prediction. So you have to remember that the model does not actually measure the EGFR mutation, or actually does not detect the EGFR mutation. It is detecting morphological features that are associated with EGFR mutation. One of the things that we noted was that the TMC data was actually, TMC images were actually biopsies and had a lot of carbon pigment from smoking and pollution, while the TC data set did not have that much carbon pigment in the images. Another thing that we are in the process of moving towards developing as an alternative to conventional testing. P16, as we know, we use as a surrogate for HPV testing. But the positive predictive value in our population is very low. It is almost less than 50%. So we are now in a process of, we have developed this particular deep learning model where on the tumor, we can predict HPV positivity with a very high accuracy and much better positive predictive value as compared to the HPV current P16 standard that we use for screening. We are in the process of developing this further and for more testing. So as of now, I just spoke about single protein, single markers, but now there are people have done large scale proteomic and genomic modeling on whole slide images. So in this particular example, they have used RNA-seq data to actually model protein expression for hundreds of proteins on the H&E slide and then compared it to the IHC expression of those proteins. And they have shown really strong results which says that morphological patterns can actually predict genomic and proteomic patterns. Now, we know that tumor heterogeneity affects outcomes. This is an example that one of our collaborators has done, and they have actually used genomic tests to quantify the heterogeneity of tumors and showed that heterogeneous tumors tend to have poor prognosis as compared to the homogeneous tumors. Now we can actually, there is this particular paper in Science reports where scientific reports where they have actually used morphology to predict tumor heterogeneity, and again shown that they can replicate the outcome prediction that was being offered through costlier and more complex genomic tests by using simply morphological features. Now, this is a work from our collaborator from US, and we are currently in the process of expanding on this work. This work was done initially on early and intermediate risk oral cancer, where they have used nuclear features of the tumor cells and built a classifier to identify patients who would benefit from radiation versus chemoradiation. And they could do this with significant accuracy. We are now in the process of validating this and improving this for late stage high risk oral cancer patients who have all received radiation or chemoradiation, and see whether we can predict which patient will benefit by addition of chemotherapy over radiation. Other prognostic markers like this, again from Anand Madabushi group from the US, where they have shown that tumor cell multinucleation is prognostically relevant. So as pathologists, we know that these tumor cell multinucleation and pleomorphic features predict that the tumor is much more aggressive. But they are now able to actually quantify the proportion of multinucleated cell in the tumor and come up with a classifier which will identify the tumor which had much more poor prognosis as compared to those who did not have a high number of multinucleated tumor cells. They again show that this is stage independent, and they have shown that this is a very good prognostic marker in HP16 positive oropharyngeal carcinoma. They actually did it on multiple data set from multiple hospitals. And the point I want to highlight in this particular table is that while they were significant in almost all of them, the hazard ratio changes significantly across the different hospitals, telling us that there are other factors that are affecting the prediction of the model, and that the generalizability of models is not an easy task that can be achieved simply by using the same scanners or same cancer types. That models may not work equally well in all the hospitals, and therefore you need to test the models at your own hospital data set before you adopt them for future use. Obviously, you can now quantify a lot of the tumor immune cells and the tumor cells and go ahead with it. And we can there are now immune scores, digital immune scores, which can predict outcomes. So this is a digital tumor associated stroma scores, digitas scores, where and digital stromal TIL scoring, where it again they are stage independent predictors of outcomes and performance. I'll skip a few of similar related slides. This is one of our work that we have done with our collaborators in UK, and now we are in the process of actually, this is done in breast cancer. We are doing now in head neck cancer at TMC. So we know that in the nodes, the tumor, the involved nodes counts and the tumor size in the nodes mattered. But we have never really focused on the uninvolved nodes. So we are now showing that the uninvolved nodes also have a story to tell. The uninvolved nodes, the level of reaction in them, the amount of germinal centers and the amount of sinus histiocytosis and the expansion of sinuses have a story to tell, and they are also predictive in outcomes. So where is all of this going? Essentially, one of the important things that this is going to go, apart from actually perhaps giving us additional prognostic markers and predictive markers, biomarkers, is that it will go try and reduce the turnaround times for many of the tests. It's going to accelerate the turnaround times and reduce mortality and morbidity associated with the delay in starting treatment. But AI models are not easy to train or to validate or to actually use. That is why currently there is no deep learning model which is actually available. Most of the, in clinical practice, most of the AI models that are currently available essentially are about some quantifying some parameter, whether it be ERP or HER2, MIB1, or the Gleason's grading. But there is no clinically predictive AI model currently available as a commercialized test or an FDA approved test. There are a lot of problems that are associated with in this process. One of the things is that you need large volume data to really be relevant and be accurate. The data has to be representative of the problem that you're trying to answer. You need thousands of slides and thousands of patient data to really have a model that can dissect through the differences and be accurate enough or generalizable enough. And there are a lot of tissue artifacts that affect the outcomes or the model predictions. The artifacts which include the cutting, the staining, and even the scanning artifacts affect the model predictions. For example, this particular image at the bottom, we can see that the same slide scanned by two different images can give different color profiles, and therefore all of these things affect the model predictions. So while we are doing all of this work, we actually realize that there is a problem that we need to solve. We need data to be ready. If we have a 2-year project, most of the time went in actually collecting the data rather than on analyzing and working on the models. And therefore, we set out to try and solve this problem for possibly for everyone, that yes, let's have Indian data put into an image bank, which we can make available to the AI researchers who want to build models that are relevant to the Indian population. So this is a project which is a multi-institutional project. TMC is the lead, but we have collaborators for AIMS, Rajiv Gandhi Cancer Center, and PGI Chandigarh, as well as the AI expertise from IIT Bombay. We are putting in a lot of data, from timeline data from the date of diagnosis to the final outcomes, and all the radiology, pathology images that come in between into this data, along with the linked clinical information, treatment details, and the other outcome data that is measured. As a part of this thing, we have come up with a lot of tools that are now being tested, and we are trying to push it into actual practice. One of them is build a quality control tool where it loops and does an automated quality check of the whole slide images as to whether they what kind of artifacts they have, how much usable tissue they have, whether there is scanning artifacts or cutting, mounting, or staining artifacts. And we have been able to actually show that if we actually use this as a pre-processing tool, we are able to increase the accuracy of the models that use this information downstream. So for example, the accuracy of metastasis prediction in the lymph node increases if we use this method to pre-process the patches and clean out all the patches which have a lot of artifacts and a lot of other issues with them.
So Swapnil, if we can wrap up in maybe a couple of minutes.
Sure. So another thing that we have done is to train AI models, you need a lot of data, not just in the images, but also annotations. A single pathologist would never have the time to do all the annotations. So we are using this pathology reCAPTCHA as an adaptation of Google reCAPTCHA, wherein we use the pathologist input at the time of login into the reporting platform to generate annotations which have inbuilt confidence levels, and then use this to train models which can predict tumor as well as tumor, non-tumor, that kind of binary classification. So this is our current status of the image biobank, and this biobank will soon be available publicly through DBT's website as well as through our TMC websites for AI researchers. There is we have been also developing a lot of our own algorithms during this process. A last couple of slides on generative AI. The generative AI, as I said, is very early. Currently, the applications that are clearly there that can use large language models or vision language models is to generate reports in a semi-automated or automated manner, or summarizing findings in images. So if you must have heard of the application called PathChat, developed by the Faisal Mahmood group from Harvard. And you can actually throw images at it, and the AI model can summarize what it sees in that particular image. There are a lot of problems with AI models which we have to deal with as we go ahead. Again, digital pathology forms the base of this, but essentially the digital pathology being the third revolution, while AI model usage is going to be the next revolution in pathology and transform the way we look at slides. That is all from me. This is my team at TMC, where we do a lot of these. It's an interdisciplinary team of pathologists, ML scientists, as well as technicians, and we do a lot of work in collaboration with the multiple organizations in and across the world. Thank you.
Great. Thank you, Dr. Swapnil. Again, the very difficult topic to cover so much ground in 20 minutes. But if there are any immediate questions that we can take, that'll be great before we just close. By the way, there was a question on the chat while we are waiting. Somebody had asked, I think Anup Roy, that can we submit slides for an opinion? So I don't know
Yes,
if it
sir.
was directed.
I'm basically very sure. So
Yeah.
we have a lot of confusions in a center in Northeastern. I'm working. We have a lot of confusions even university filings on these things.
You're not
Can we
very,
get it,
not very
suppose-
clearly audible, but
Arup.
if you're looking for a second opinion service with digitized slides,
Yes.
we had thought of doing this, but there were a lot of issues that still need to be sorted, including normally when you submit blocks, we also do our own IHCs and any additional stains and whatever else that we would need to give an opinion. But when we do only digitized slides, we don't have access to the blocks. Then the opinion becomes kind of limited based on whatever is available. And because we don't control the pre-processing steps, neither the cutting, staining, block processing, or the digitization process, it becomes difficult to legally. I mean, there are a lot of arguments that there could be legal issues and things like that. But it is one of the things that we would like to do. But currently, there are a lot of issues, regulatory as well as technical issues that need to be sorted before this can be done. We are happy to actually share slides that you have given to us, blocks or whatever, and we have digitized, and that we can share. But reporting only on digitized slides that you provide is going to be a difficult task because it is an incomplete information being provided.
Okay, if we submit blocks, then is it okay?
If we submit blocks, then is it
Yes,
okay?
yes, we get blocks from across the country. There's no problem. We get blocks by post also. So 30% of our work is external reference. So we get blocks from everywhere, and you can send the material with relevant clinical information
and we'll share the details with you, Arup, if you can write back to us on, if you see in the chat, no, there's an email address. You can do that as well.
This is Satish and Dr. Swapnil.
Yes.
Great talk, Dr. Swapnil. It is a wonderful one.
Thank you.
I want a few clarification regarding this annotations. You said to facilitate software is available. Can you just elaborate on how it is done?
To do annotations, if you want to do your own annotation on your own files, there are many free tools available. One of the best ones that I recommend is QPath. QUPATH. It's a free software and it's continuously upgraded and maintained by a team in the Europe. And it's one of the best tools that are currently available in the AI research domain for digital pathology. That is my state. So it installs on your PC, and you can do that. If you're once you go beyond, if you're working in a single institution, single location mode, then this is more than enough for most scenarios. But if you want people working across multiple centers who annotate and give you annotations and things like that, then you need some more tools. That obviously will come with some expense and some things. But even then, QPath is very versatile. People can use it across the board, but they won't be able to work on the same files simultaneously. If you want one application that can work in a network mode, there is an application called Pathomation. It's a Belgium-based software. It is the annotation platform is not free, but they have a vendor-neutral image viewer, basic image viewer, which is freely available for you to try out on your desktop.
Thanks, Dr. Thanks.
Okay. I think in the interest of time, we'll bring this to a close. Just a reminder that we will keep doing these kind of webinars once every 3 months or so. So if folks on this call have other topics that they're interested in, or if you yourself are working on something interesting that you feel will benefit the broader community from a digital standpoint, the idea is really to evangelize the work and see if some collaboration efforts can be initiated. But as a specific follow-up, at least we will discuss if we can form a working group on digital pathology that can focus more on standardizing and figuring out how we scale these initiatives. We will take that as a follow-up. Again, thank you everyone for giving your time. Especially thanks to Dr. Joy and Dr. Swapnil for putting in the effort to put all of the content together. Have a good weekend.
Thank you.
Thank you.